On the screen are Augustin Cauchy and Bernard Riemann, the first and second names respectively in a field of math called complex analysis. Complex analysis is a rich field of mathematics that starts by taking the theory of calculus and instead of thinking about functions from R to R, thinks about functions that take in and spit out a complex number. It's been around since the 19th century but is still relegated to undergraduate mathematics. Part of this is because there's a common refrain about complex functions. You can't graph them. The argument typically goes that because C is R2 as a set, a graph of a complex function would live in R4. And so, there have been many different ways to visualize these functions, and these videos here go into depth into many of them. Something you might notice about most of these methods is how reliant they are on computers and electronic technology. And in this video, I want to talk about a way to visualize complex functions that Cauchy himself could have done in the 19th century. For the first part of this video, all I'm assuming is familiarity with complex numbers, but as we go on, the math will ramp up. So before we begin, let's quickly review what a graph is and how to graph a line. A graph of a function is colloquially a single picture of information of a function inputs and outputs. You can easily see what input goes where, and we don't have to spend a lot of time on this. Particularly easy functions to graph are lines. If we have something like y equals 2x plus 3, we can just plop a dot on the y-intercept, plop a second dot on the y-intercept plus the slope, and connect them with a line. Grade school stuff. So now that we've thought about a real case, let's do something analogous for the complex case. Let's take this line. Y equals 2 plus 2i all times z plus minus 1 minus I. Let's start with this grid on the bottom, and we're going to put another grid on top. On top, I'm going to plop down a point on the y-intercept, minus 1 minus I, and label that 0, because 0 gets mapped to minus 1 minus I. Then I'm going to add the slope, 2 plus 2i, plop a dot down, and label that 1, because down here, this is where 1 gets mapped. Next, I'll connect them with a line. Departing from what we did before, now I'm going to rotate this line segment 90 degrees around the y-intercept and label this endpoint I, because this is where I gets mapped. And then we can extend these lines like so. And if we want, we could get a grid like this. And this here is a graph. It contains all of the information about inputs and outputs in a single picture. By construction, we labeled where 0, 1, and I get mapped. But what if we want to see where something like 2 plus I is mapped? Well, we would go along 2 on the top grid and up 1i on the top grid and see where we are on the bottom grid. And as we can see, both geometrically and algebraically, it's 1 plus 5i. So, if a graph is a single picture that captures both the inputs and outputs, then that's what this is. Similar to how in the real case, where horizontal lines and vertical lines are inputs and outputs, respectively, this top grid represents our input space and the bottom grid represents the output space. And so if I want to see where a plus ib is mapped to, I walk along the top grid along the real axis by A, and then the imaginary axis by B. And then I see where I am on the bottom grid. Now it's worth thinking about what horizontal and vertical lines mean in this context. In the real context, a vertical line is very steep with a big slope, and horizontal lines are ones with small slopes, like these. So, what if in the complex case we just took it to be the same way? I made a GeoGebra applet to help me write out these graphs that you can play with, which I put in the description, but the underlying method is still pencil and paper. Well, if you graphed lines with smaller and smaller complex slopes, these grid lines get closer and closer together, and you can imagine that in the limit you have an infinite number of these points around the origin. So I'll leave you to think about this. What does a vertical line look like? That is, a complex line with an infinitely big slope. Anyway, back to the main topic. If we have this new idea of lines, we have to think about what intersection means in this visualization. So let's just really quickly think about what it means for two graphs to intersect in the real case. Well, this is quite simple to visualize, but it might be a bit harder to describe. It's just obvious where these two lines intersect, like why is this even a question? But algebraically, we can describe it as the same input giving the same output. Now, let's bring it back to this idea of the same input giving the same output to the complex case, where the same walks on top give the same place on the bottom. Here I've graphed these two lines, but there's so many intersections that it's hard to see where they truly intersect, but it is in the picture. If we worked it out algebraically, which works exactly the same as it does in the real case, we'd see that they intersect here, where the second coordinate is -1 minus 3i. And indeed, in this picture, these two walks of -1 minus I give the same place on the bottom. And to wrap up this section, I want to emphasize that this method of graphing isn't restricted to just lines. You could sketch out a complex parabola and do something similar. Here is just a small graph of this complex parabola and a table of values. Now, as an exercise, see if you can use Newton's method to estimate what the zero of this parabola is. Now, if you want, this can be the end of the video. I hope I convinced you that complex functions can be graphed and visualized in this elementary way, and you can go forward with this. On the other hand, others might be saying, well, so what? Because at the end of the day, this is just what's called curvilinear coordinates, and you could read about it on Wikipedia here. Well, so far I've described a geometry with these points and lines in C2. But if we have lines and intersections, we need a way to quantify these intersections. But how can we do that? Well, in a complex vector space, the way this is done is with what's called the Hermitian product. So if we have these vectors in C2, then their Hermitian product is this kind of weird sum. It's not super obvious where these complex conjugates come from, but it turns out to have quite a nice geometric interpretation, but this requires a specific type of visualization of C2. To visualize a vector in C2, say this one up here, all we have to do is plop down the components like this. I like the first component to have a circle at the end and the second to have a cross at the end. Now we can put down a second vector, such as this one. Now what we'll do is we'll take corresponding sides and draw parallelograms. Now we're going to take the signed area of these parallelograms and add them up. What that means is that if the second component is counterclockwise to the first, then the area is positive. And if it's clockwise to the first, then it's negative. And then we add them up. And what's crazy about this is that this value of added signed area is exactly the imaginary part of the Hermitian product. This value has a special name. It's called the symplectic product, and it works much like the dot product. Now, what I find somewhat remarkable about the symplectic product is that, unlike the Hermitian product, for us humans, it's the most obvious geometric information about complex vector spaces. For our case, for a given vector in a complex vector space, we can ask about the symplectic orthogonal complement, basically the vectors that are perpendicular in this symplectic sense. So a natural question is, given a complex line, what other complex lines are symplectically orthogonal to it? Well, for this, it's useful to think about the real case. So if we have real lines like this, any pair of vectors, one coming from each line is perpendicular. Their dot product is 0. So we want the same for complex lines. In other words, for a given complex line, what is in its symplectic complement? For any pair of complex lines, any pair of vectors, one coming from each, must have 0 symplectic product, per our definition. So what can we immediately deduce? First is that the area of the second parallelogram must be the negative of the area of the first parallelogram. Second, if the first component of each vector is 1, then the second component is going to be the slope. And already we see that if the symplectic product has any hope of being 0, the slopes have to be real multiples of each other. Otherwise, we're adding 0 area with some non-zero area. But this isn't enough. We want all points on one line to be symplectically orthogonal to all points on the other, not just these two. And so, we're going to work out some of the trigonometry using this formula for the area of a parallelogram. We deduce that two lines are perpendicular if and only if one slope is the original slope multiplied by the negative reciprocal of the square of the length of the original slope. Now, this might be somewhat of a convoluted formula at first, but if we do some additional algebra, then we get that the slope of the symplectically perpendicular line is the negative reciprocal of the complex conjugate of the original slope. So, when the slope is just a real number, we get back our original formula for the slope of a perpendicular line. Now, Symplectic geometry goes much deeper than this, but it typically isn't presented this way. Historically, it has its roots in physics, but as a math person, I find it to be much more compelling to say it's the geometry about complex lines and their intersections as described by the symplectic product. I could go a lot deeper, particularly about the subspaces of symplectic space, but for now I hope I've convinced you that this way of visualizing complex functions naturally lends itself to symplectic geometry. Thank you for watching. The last thing I want to mention is that as far as I know, there isn't really an agreed upon axiomatization of complex planar geometry with the symplectic form. This is one possible axiomatization, so to any particularly interested viewers, try playing with these, see what you can find, and it's probably going to be novel.